All right, so let's take a look at one like this. How about what am I going to do?
You want to change it to powers?
Good. What else can I do? Because right
Oh,
now,
you can add them, you can do additional things.
yeah, we'll exploit properties of logs there, right? So we can avoid having to do the product rule. Does that make sense? So this just becomes natural log x plus what?
One half.
Okay, so yeah, so 1/2 natural log x squared minus 1, right? Okay, and that helps. Now when I differentiate, what's that?
Aren't you supposed to, this is the part I'm confused on. When we put the 1/2 in front, usually when we do that, don't we have to, oh, it's because you're not doing chain rule, is it, with parentheses?
Right.
Oh, that's where I was. Okay.
See what I'm saying? Yeah, and so real quick, the derivative with respect to x of natural log u is what?
U prime over U.
Right. Okay, so what do we get here then? We'll differentiate this term. Over,
X.
okay, good. Plus, what about here? So I've got my 2 on the bottom. I'll just collect it on the bottom. What's the derivative? So what's u prime?
2x.
And then on the bottom,
Squared minus 1.
right? That make sense?
I was confused as to why you don't, because you have the x minus 1 to the 1/2, so I was confused as when you put the 1/2 in front, why you don't subtract 1 from the 1/2 and get -3/2.
Because it's not a power now, it's a coefficient. See what I'm saying?
Yes.
Okay. I mean, we could have left it there, but then that makes the derivative, it would have worked, right? If I had left this instead as the square root of x squared minus 1, that's kind of a pain, right? Then I've got to take the derivative of a square root to get my u prime, right? See what I'm saying? And you kind of look ahead, what's going to happen? You can see that when you take the derivative of the square root of something, I'm going to get a -1/2 power, which moves it to the bottom as a square root on the bottom, times 1 over the square root. That's where the square roots cancel, right? But that's a lot more work. You want to exploit the properties of logs to make it easier first, right? Okay, so which brings us to the technique of logarithmic differentiation. Okay, so let's take an example, like what would we do, what if we had something like this? Say we had the function y equals x minus 2 squared over the square root of x squared plus 1. And we want to differentiate that. Okay, that's a mess, right? You guys did a bunch of stuff like that earlier in the year. That's a mess because there's so many layers to this derivative, right? You've got a quotient, and then you've got, within the quotient rule, you've got chain rule stuff going on, right? Okay, but we could make this a lot easier, and this is something that we talked about last week that you guys weren't here for. One of the nice things about properties of logs is that logs effectively move. When you take the log of an arithmetic expression, it moves it down the complexity ladder 1 rung. If you think about this. If we were to categorize the operations of addition and subtraction, multiplication multiplication, division, and exponentiation, it would go sums and differences are on the bottom rung, products and quotients would be the middle rung, and exponentials would be the top rung, right, in terms of difficulty. Well, when you'd use your properties of logs, it moves everything down one rung, right? But there's no rung to move from. If you're already on the bottom rung, you can't do anything. There is no property of logs that you can rewrite it, use to rewrite it, right? And this just goes back to from last year. Remember that the log, any base log of a product becomes the sum of the logs, right? Remember this stuff?
A little bit.
Right, so that's a property. The log of a quotient is equal to the difference in the logs. And the log of a power equals the product of the exponent times the log. So it moves everything down a rung. But there is no property for a sum or a difference. Can't do anything with that. There's no place to go. Okay, but we could use these properties to our advantage here. So this is a process called logarithmic differentiation. So when you see something like this, where you've got a function that's defined as some amalgamation of products and quotients and exponentials, you could just take the log of both sides to make that simpler. Now, it's not going to help you if this is a sum at some level also, right? Because then you can't go any place with it. But like this, look at this. We've got a factor on top, we've got a quotient, and the numerator and the denominator are both powers of an argument. That's a 1/2 power and that's a 2 power of 2, right? So if I log both sides, I'm going to be able to do lots of stuff to make that simpler, term by term, right? So we're going to get, whoops. You tell me, what can I do to this to rewrite this using properties of logs? Okay, so I can subtract. I've got a quotient first, right? So I could rewrite that as the log of the numerator.
If you use like multiple logs, like let's use one, can you keep?
Yeah.
You can't.
Yeah, we can keep going. So I get the log of x minus 2 squared minus the log of the square root of x squared minus 1. And that's going to split into, this becomes 2 times the log of x minus 2, right? This becomes 1/2 times the log of x squared minus 1, right? Okay, now, remember,
Yep.
if I implicitly differentiate with respect to x, both sides,
Sure.
what am I going to get on the left side?
Y times x. X.
What's our rule for the derivative of log u with respect to x is u prime over u, right?
Right.
So what's the derivative of log y with respect to x? It's just going to be the derivative of the argument divided by the argument of the log, right? So if that's a y, what is it?
It's 1 over y.
Well, y prime over y, right? Okay, so we end up with y prime over y equals, what's the derivative of the first term? The derivative of log x minus 2
Y over x minus.
is just 1 over x minus 2,
Yeah.
right?
Yeah.
But then I'll multiply the 2 through and get 2 over x minus 2 minus derivative of log x squared minus 1 is going to be 2 over 2x, right, over x squared minus 1 times
2, so
1/2, yeah. So those cancel, right? And so then look at that answer, that was easy, right? Now we know that y prime, if I solve for y prime, that's just gonna equal all this stuff. 2 over x minus 2 minus x over x squared minus 1 times y. And what's y? Well, y's just that, right? So I can make that substitution and I'm done.
For the bottom fractions, you have a positive and you change it to a
Where's that?
negative. So for the x squared minus 1 is supposed to be x squared plus 1.
Oh, it is?
Mhm.
Okay. Up here. All the way through, that was supposed to be
Yeah.
x squared plus 1. Yeah, it was. Okay, it didn't change anything. But yeah, okay. And then I could either plug that in or just leave it defined as y. Make sense? Okay. So that process is logarithmic differentiation. Okay.
Oh yeah. When you are dealing with logs and stuff, and you have two parentheses, so like say x minus 1 times by x plus 1, do you always want to multiply them together to get x squared minus 1? Or would to make it?
Well, I would, because then you don't have to do the product rule. Yeah, if I understand your question.
Yes.
Okay. What else should I do here? I think you guys are pretty good on this. The only other thing I'll show you here, and this is really minor. So we have this definition. You gotta think in terms of what a natural log graph looks like. So we have the derivative rule. Derivative with respect to x of natural log u equals u prime over u, right? Well, what's true of u though?
Me is smart.
U is smart. If you think about what the argument, what a natural log function looks like, what's the graph of a natural log function look like again? So it's asymptotic on the negative y-axis,
Yes.
right? And it's gonna go through the point 1, 0, right? And it's always concave down. Okay? Make sense? It's not defined for negative arguments though, right? U has to be positive. It's not defined for 0. So what would it do if I did that? Does that change anything? Because sometimes we'll take functions that could be negative valued, and in order to take their log, we'll take a log of just the absolute value of u. Do you see that that's not gonna change my answer at all though? Right? Because we already make that presumption with a natural log function that the argument has to be positive or it's undefined, right? So if there's an absolute value around the u, around the argument of the natural log, doesn't matter. The answer is still just u prime over u. Okay, so for example, what if you had something like this? What if you had the derivative with respect to x of the natural log of the absolute value of cosine x. What's that equal to? It's just u prime over u. What's the derivative of cosine?
What?
Over cosine x, which is negative tangent x. That's it.
It's absolute value, isn't it?
How is it?
Uh, no, because what we're finding is a derivative here.
Okay.
See what I'm saying?
Kind of. That's good.
So if the absolute, what does the absolute value of cosine look like? So if we were to graph cosine function, what's a cosine function look like? Cosine function just looks like this, right? Does that make sense? Okay.
Correct answer.
And so the derivative of this is going to be defined as the slope of the log of this function, right? Okay, so if I take the absolute value, that's just going to bounce it off the x-axis,
Okay.
right? See what I'm saying? And so if you're taking the natural log of that, it's, how do I say this? It's still going to be defined as this ratio though, because there's no real good way to articulate this for the best way to say it, I think, is that you know that because you're taking a log of a function and the log is not, it can't even be defined for a negative value of the function, right? Its derivative is going to be unaffected by the fact that the absolute value sign is there because it has to be that behavior anyway. So kind of the short working rule of this is, the good news is you can just ignore the absolute value. It doesn't change anything because it's already implied. Okay?
Okay, Mr. White,
Mm-hmm.
I have a question.
Mm-hmm.
Well, because this is the one time when I think it should be right. So, it's a pretty simple problems, like you don't need to do like all the basic parts.
Mhm.
But number 6,